Vanakkam. Welcome to this course on biomedical instrumentation. In the previous set of videos, we have been looking at EMG. We will continue our discussion of EMG and look at some matters of detail, practical detail when it comes to EMG recording. We will look at some illustration data and what is RMS of EMG, how does contraction of muscle relate to EMG, this and potential surface electrode that you are measuring, what is the meaning of differential recording, differential electrode based recording, and what are the factors that influence signal measure, some practical considerations. So, this is the class that you need to be, that essentially separates the experts from the novices. This is the critical class in EMG, because this one, if you know all these things, all these concepts, you are essentially a top skilled, not necessarily execution, not necessarily someone who can measure EMG, but someone who is who has top skills in at least the theory of EMG. Note that the neurophysiology of EMG is beyond the scope of this course, is there in my other course on neuroscience of human movements. So, what are these? Electrical signals that are generated in the muscles are called as muscle action potentials, and more specifically those that are generated in individual motor units are called as motor unit action potentials or MUAPs. These also travel along the muscles, that is why they are called as MUAP trains or MUAPs or MUAPs. Okay. These are the motor unit action potential trains. These electrodes are usually placed on the surface of the muscle, or in case of indwelling or needle electrodes, sometimes inside the muscle tissue. What do they measure? They essentially record the algebraic sum of motor unit action potentials. Algebraic sum means what? Algebraic sum means sum with sign included, SIG and sign is included. Okay. Algebraic sum of all motor unit action potentials that are being transmitted along the muscle fibers. Muscles are composed of several motor units. Each motor unit is controlled by one and exactly one motor neuron. Each motor unit, the definition of motor unit is that a motor neuron and the set of all muscle fibers that it innervates together essentially constitute a motor unit. So, each motor unit is controlled by one and exactly one motor neuron. This motor end plate is essentially the synaptic junction between the neuron and the muscle fiber or the set of all muscle fibers. This is the several neuromuscular junctions exist. So, whenever this postsynaptic membrane is depolarized, when will this be depolarized? You need to check my video on neuromuscular junction in my course on neuroscience of human movements, in which I describe in detail, quite a bit of detail as to how this is happening. Okay. Let us just say that the postsynaptic membrane, what is the postsynaptic membrane in the neuromuscular junction? The muscle fiber. The muscle fiber, when it depolarizes as in the case of activation of the motor unit. Whenever the motor unit is activated, whenever the motor neuron is activated, all the muscle fibers related to that are depolarized. All of them produce an action potential after a time delay. Right. End plate potential is the potential that is recorded, but then there might be several such motor units and several such end plates. Right. So, what you are measuring is the depolarization wave, is the result of depolarization happening in several motor units approximately. By the way, they might be having different timelines, they might be at different phases of their own conduction. So, what you are measuring is essentially the ensemble activity of multiple motor units. This depolarization wave essentially moves along the direction of the muscle fibers. Right. the signal that you are measuring between two EMG electrodes. Remember, this is bipolar recording. Differential signal that is recorded between two EMG electrodes essentially corresponds to the wave front and to the subsequent repolarization wave. It's a difference between these two. Okay, we will discuss that in a bit more detail. Root mean square is a widely used. So, what you use root mean square is quite often used to quantify how much amplitude is there. It reflects the overall intensity of muscle contraction. Why does it matter? It's EMG signals are bipolar because it also has negative. So, RMS essentially converts this into a positive value. It is not an accurate measure, it's an approximate measure. Okay. It provides an approximate measure of muscle force and motor unit recruitment and fatigue and recovery tracking if you want to do. It is extremely valuable in clinical, even today it is used in clinical diagnostics and in sports science and in biofeedback system. Okay. Even today RMS continues to be one of the metrics in these fields such as clinical diagnostics, sports and biofeedback systems, which is quite often used. We already discussed how this happens. Alpha motor neurons essentially fire signals to initiate the contraction of the muscle, and motor units are activated in the order of size from smallest to largest. This is called as the size principle or the Henneman's principle. Beyond the scope of this course, I have discussed this in my course on neuroscience of human movement, Henneman's principle. Please check what this is from a video on size principle in neuroscience of human movement. Essentially, it increases the number of fibers that are contracting as the amount of force required keeps on increasing. And how a sarcomere produces force is beyond the scope of this course. Essentially, here is a relaxed sarcomere, here is the contracted sarcomere. This is a relaxed sarcomere. Essentially, what is happening is that there is the actin myosin bond that is formed and pulling that is happening, that is reflected as a contraction. Many such contractions simultaneously happen, producing this muscle contraction and force between. This is the contracted sarcomere, this is the relaxed sarcomere. Okay. Essentially, actin and myosin filaments slide past each other. This theory is the so called sliding filament theory. Again, the details of this I have a separate lecture, nearly half an hour 45-minute lecture on sliding filament theory in my other course on neuroscience of human movements. But what is sufficient for you to know is that force, as the force generation increases, the contraction strength increases and the EMG amplitude increases. This is sufficient for you to know. So, that means force is generally proportional to EMG amplitude. Proportional does not mean that it is linear, it is linear in a small range. Okay. But what are you measuring at the surface? What you are measuring at the surface is this voltage V. But what is actually happening is that what you are interested in, you are interested in the magnitude of this depolarization wave. You are interested in this. This is of interest. This is the quantity. This is the quantity of interest. This is what I am interested in, but this is what I am measuring. I am interested in M, I am measuring V. And there are other things. There is a constant of proportionality K and a solid angle that is subtended at the electrode by the wavefront area. So, the depolarization wave is travelling in this direction, the electrode is here. What I am measuring is essentially dependent on the constant K and the angle as the depolarization wave is approaching, the electrode is going to pick up a larger and larger signal. As it is leaving, it will show a negative signal as it is leaving the electrode. Suppose this is the direction of the contraction or the depolarization wave. And there is a depth of, in relation to that, there is also a depth of the wave below the skin surface. Remember that this has all the things subcutaneous fat, many other layers in between, all of which we do not have a model for. In the electrode theory also we did not model this. We said there are some things, there is the resistance and capacitance, we said that. And then there is the area of, this is the surface area, this is the area of the depolarization wavefront, this is the area. Okay. I am interested in measuring M and I am measuring V. So, essentially from V I will have to compute what M was, an inverse problem, okay, because I do not know omega. I may know K, I may be able to numerically compute K, I may make many measurements and then numerically compute K, but for each measurement I do not know omega. So, it is an inverse problem that is substantially difficult to crack. Okay. Note also that depolarization is a rapid process, depolarization happens very fast, is a quite a rapid process. So, the leading edge of the wavefront is usually sharp and the magnitude of the motor unit action potential during depolarization is usually very big, whereas the repolarization in comparison is actually a slow process. Okay. The leading edge of the wavefront is usually not sharp and the magnitude of the motor unit action potential is relatively small when compared with depolarization. And we have only looked at one electrode so far, because in the previous picture there was only a single electrode, okay, but most EMG systems require two electrodes placed over the muscle and you are essentially measuring the difference between these two electrodes, is it not? Because it is a differential electrode, differential amplifier configuration. The voltage waveform that is recorded is the difference between the in the potential between these two processes. So, essentially I am having a potential electrode that is placed here, that is measured like this and then like this, and suppose this is the direction of the waveform. There are two electrodes, electrode 1 and electrode 2, and that is the direction of the wavefront travel, and I am picking up this depolarization wave in VA first followed by VB, that means that will be a phase lag. But what I am amplifying is the difference between VA and VB, which will be this, is it not? Because there is a phase lag, right. The differential electrode essentially subtracts VA and VB to reveal what is the true biological activity that is happening between this point and that point. What is the true biological activity that is happening? These voltage waveforms at each electrode is almost the same, but not exactly the same, because there might be some new activity that might come in here. Between these two electrodes some new activity might happen. So, it is not exactly the same, almost the same, but shifted in time. The similarity between these two waveforms will be relatively high when the electrodes are kept closer. If the electrodes are far away, then the similarity will be very, very low. So, the differential signal between these two electrodes is smaller when the electrodes are located near to each other. So, that means there is such a thing called as optimal inter-electrode distance. There is such a thing where I am going to get, best possible signal for, by the way, this is expected to vary between muscles because different muscles are of different size, okay. But there is such a thing called as optimal inter-electrode or between electrode distance. And what are the factors that influence the signal measured? Electrode size. What is the size of the electrode? Is it a circular electrode? What is the shape of the electrode? Is it a button type circular electrode or is it a cuboid? Not this. Distance between the electrode, I already mentioned this. Electrode separation distance with respect to the muscle tendon junctions. No, this is not electrode separation, this is not inter-electrode distance, but rather the distance of the electrode with respect to the muscles themselves. That thickness of the skin and subcutaneous fat, something that you cannot control. How much fat a person is having, you do not control that. Misalignment between electrodes and the fiber alignment, fiber direction and the electrode direction. If it is misaligned, there is going to be more noise. And then there are other physiological factors that come into the picture, blood flow and temperature, type and level of contraction, whether the person is doing isometric contraction or whether the person is doing some other type of contraction, whether the person is doing concentric contraction or eccentric contraction. What are these types? Do check my other course on neuroscience of human movement. And conduction velocity, and the number of motor units that are active at a given point in time, how much force is being produced, depending on that the number of motor units that are recruited may vary. That, and the amount of motor unit synchronization, how these motor units are synced with each other or not synced with each other. All of this affect the signal that you are measuring, but what you are measuring is a signal that is affected by all these things. Okay. With this, we come to the end of this video. In this video, we looked at surface EMG, root mean square, some illustrative data, and how muscles contract, and what is the potential of the surface electrode, and how is it related to the actual motor unit action potential that is of interest, and what differential recording means, and what are the factors that affect signal that is measured. With this, we come to the end of this video. Thank you very much for your attention.